In this very short video, we're just going to define what induction is. It can be called weak induction or induction. Later, we're going to talk about strong induction. And it depends on which textbook you look at or which person you speak with. I usually just think of the first one as induction, or the principle of mathematical induction. And the second one that we'll talk about, strong induction. Well, some will call the version I call induction, they'll call it weak induction, and then what I call strong induction, they will call regular induction. And it doesn't matter. The proofs would look different, and it would be obvious by looking at a proof whether induction or strong induction were used. And we'll get to that more when we talk about strong induction in a future video. But the principle of mathematical induction, or weak induction if you'd like to call it that, is analogous to this simple example. This is a bunch of dominoes that are lined up. Maybe we're looking at the side view, and each one of them is numbered. Think of it being starting at 1, 2, 3, 4, and going on infinitely. Well, and also, by the way, they need to be spaced so that they're less than the height apart. So if I knock 1 over, 2 is going to get knocked over, and so on. Well, now that I've said that, if I knock over domino number 1 to the right, it's going to hit domino number 2 and knock it over. Number 2 is going to knock over number 3. Number 3 is going to knock over number 4, and so on. And if I picked randomly 1,000, that one's going to get knocked over. And it's all because number 1 was knocked over. Knocking over number 1 will cause every single domino in this infinite list to get knocked over. That's a little bit like the principle of mathematical induction, and you'll see why in just this simple definition. Okay, the induction axiom, or weak induction axiom. I'll have to define all these terms. P1 and P2 are just propositions corresponding, this one to number 1 and this one to number 2. Let's make a real simple example. Proposition K is the proposition that K is an even natural number. Real simple. P of 1 would be false. 1 is not an even natural number. P of 2 would be true. 2 is an even natural number. All of the odd ones, P3 would be false, P4 would be true, and so on. So we have an infinite number starting at P1 of propositions corresponding to this number in the parentheses, infinite number of them, and all this proposition is a true or false statement. So let proposition P1, P2 be statements, true or false statements. Here's the induction. If the first one is true, P1, and if this statement holds true, if P of K being true implies P of K plus 1 is true for all the natural numbers K, then what can we say? We can say that P in is true for all natural numbers n. We can say that every single one of them is true. How does that apply to the dominoes? Well, P1 being true means 1 gets knocked over to the right. And I can also say for any value of K, for example, K being 1,000, if domino 1,000 gets knocked over, that means that domino 1001 is going to get knocked over as well. And then if 101 gets knocked over, that means the next one, 102, 1001 implies 1002 is going to get knocked over, and so on. So the mathematical induction, very, very powerful proof for proving a formula is true for all values of n. And before we get to examples, which will be in the next video, I'm just going to make one more statement. We're not going to prove this, but theorem. Well, the well-ordering principle that I call WO and weak induction, which we just defined, are equivalent. All that means is that if weak induction works, that implies the well-ordering principle is true. If the well-ordering principle is true, that implies weak induction is true. So they're just two equivalent statements, and it's not a difficult proof, but I'm not going to spend the time to show the proof that the well-ordering principle and weak induction are equivalent. And next video, we'll start our series of mini examples.